Okay, hello all and welcome to this discussion on the high pass filter that you will be doing as part of this lab session here. Okay, so in the theory, we discussed the uh, and analyzed the low pass filter in great detail. Okay, so this was the R, this was the C, and this was my V out of T. Right, and essentially we said that the differential equation, right, so basically V in of T at all times has to be equal to the voltage across the resistor VR of T plus V out of T, right, and VR of T is going to be I of T into R, so V out of T, and so if this is I of T, then I of T is going to be C into dV by dt. So you get RC dV out by dt plus V out of T and this thing, right. Therefore, you can write the differential equation of the low pass filter as dV naught by dt plus 1 over RC V naught of T plus equals V in of T by RC. Okay. So this is my low pass filter. Now what you have been asked to do is to analyze the high pass filter. Okay. So you basically get the high pass filter is the opposite. You first get the capacitor and then you get the resistor, V in of T, R and C, and this is my V out of T, right, and therefore my Vc of T across the capacitor is V in of T minus V out of T, right, and therefore if I want to now relate this V out of T, right, so what do I have to do? Again, you have a current through here which is I of T, and V out of T is simply going to be R times I of T. Okay, and what is so V out of T, and what is I of T? It is C times dVc of T by dt. Okay. So implies I can combine equation, this is equation 1, 2, 3, I will combine equation 2 and 3 and put it into 1, right. So what will happen is my I of T, V out of T is going to be I of T into R, so therefore you get RC into dVc by dt, which is basically going to be d by dt of V in of T minus V out of T, right, and yes, so what do we get here? We get 1 by RC V out of T dV out by dt plus this equals d by dt of V in of T. Okay, let us just check the equations once. Yeah, V out of T is this. I have brought RC to the left hand side divided by RC, and then I have just brought the dV out of T by dt to the left hand side. Okay, and therefore this is my high pass filter equation. Now what the problem that we did in the earlier lectures, right, was for the low pass filter, right, plus 1 by RC V out of T equals 1 by RC V in of T. This was my low pass filter. right? We essentially took the case of Vn of t equal to a sine omega naught t, right, for a particular omega naught frequency, and we went ahead and solved the differential equation, right? So if you now substitute, if Vn of t happens to be a sine of omega naught t, right, then my low pass filter equation would have simply become dV out by dt plus 1 by RC V out of t equals a by RC sine of omega naught t, right? And this we were able to, we showed you in the lectures how to solve this differential equation from scratch, right, using integration by parts and all that, and then we found that V out of t was going to be some a by root of 1 plus omega naught squared r squared c squared, right, into sine omega naught t plus phi, some phase difference, and I believe tan phi was omega naught or c. I think this is correct, because if it was low frequency, then the phase shift should be small, right, and therefore I believe this is also correct, right. So we were able to show this for the low pass filter case. Now if you take the same equation, right, for the input of a sine omega naught t, for my high pass filter, what would I get? I would get dV naught by dt plus 1 by RC V naught of t, okay, equals d by dt of sine omega naught t. So you get a omega naught cos of omega naught t, right. Now this is very interesting, okay. So first of all, let us make sure that dimensionally we are consistent with both differential equations. R into C is ohms into farads, and that's a unit of time, seconds, right. So for the low pass filter, it is dV naught by dt, voltage by time, plus V naught by RC, again voltage by time, equal to 1 by RC, again divided by time into voltage. So everything is voltage by time on the left hand and the right hand side. For the high pass filter, it is dV naught by dt, which is again voltage by time, 1 by RC times V naught, which is again voltage by time, and on the right hand side it becomes voltage by time because of the derivative of the input, right. So anyway, so even here you get this a omega naught, which again is 1 by time, right. So a is, so the amplitude which is in volts divide into omega naught, which is inverse of time, and therefore you get voltage by time again, right. So the differential equations are consistent, and you can go ahead and solve this differential equation in a manner very similar to what we did for the low pass filter, right. So it's very straightforward. You can actually you will get an equation. I will leave it to you to figure out what that equation should be, right. You can even guess, right. Now in any case, my the reason I am doing this particular lecture is to sort of give you some insight into this whole filtering process, okay. So if you look at the low pass filter, right, you look at the differential equation here, right, that we have, and you look at the differential equation that we have here. Now you just observe only the left hand side, right, only the left hand side. Yeah, both of them are identical, right. Now when you say equal to something, we are just saying it's an input to that system, which is a which has that differential equation behavior and stuff like that. But essentially the system is behaving very similarly because both have the same differential equation, right. And that means the only thing that we are doing to these two systems is to give a different input itself, right. In the low pass filter, we are giving a sine omega naught t by RC, of course, and in the high pass filter case, we are giving a omega naught times cos omega naught t. So forget sine and cos, that's just a phase difference of pi by 2. So otherwise it's actually the same input that we are giving to these two systems, right? Except one is being scaled by omega naught, other is being scaled by 1 by RC, right? So therefore, can we first of all even guess that this is going to behave like a high pass filter, right? Can we guess the behavior of this whole thing, right? So first of all, what you notice is on the right hand side, the input that we are giving is actually a omega naught cos omega naught t, right? Which means if the signal is of higher frequency, you are amplifying this by a higher value. Omega naught itself is higher and therefore you are amplifying this even more, right? So what is going to happen is you are now doing something to this input, right? The V in of t, you are amplifying it, you are doing something to it, you are actually doing differentiation d by dt, right? And then I am going to pass this through a low pass filter, right? That is what is actually happening there. So this block here, which is the derivative block d by dt, is causing the input at this point to go up proportional to omega naught. That means higher the frequency, higher the input to this low pass filter, right? And which means that now in the compared to the low pass filter case itself, where V in of t was being given to the low pass filter, we are now amplifying the input proportional to the frequency and giving it to the low pass filter, and then the low pass filter is still doing its own job of filtering that signal that's coming in, right? This low pass filter doesn't know that it's coming from a derivative or whatever, right? It is going to filter that signal just like a low pass filter. So what is actually happening in a high pass filter is some low pass filtering itself, okay? And essentially what we are able to appreciate here is that, if you just look at this equation, this whole differential equation here, where we have a omega naught cos omega naught t, it says that higher the frequency, higher the amplification factor because of omega naught. But that is telling us that if I just take the frequency to gigahertz, that means I am going to amplify it so high, that means I should get an output which is as high, not really, right? So in some sense, because it is trying to do some low pass filtering on that signal itself, right? What is happening is the input is getting scaled up by a factor of omega naught because of the derivative, and then the low pass filter is trying to do something which is trying to nullify this effect. So if you take this expression that you got here from the low pass filter, right, you just take this particular expression, which one I am talking about, this expression, right? If you take this expression of the low pass filter and just assume that now omega naught, okay, assume that omega naught, if omega naught is much greater than 1 over RC, okay, it's a much higher frequency than the time constant of that system, then this V naught of t will simply become A divided by omega naught RC, because this omega naught omega naught into RC will basically be much greater than 1, right? This is basically saying omega naught into RC much greater than 1. So therefore that 1 plus omega naught square R square C squared will simply become omega naught squared R squared C squared under the square root, and it will just come out as omega naught RC, right? And then there is this sine of omega naught t plus phi, right? But effectively, what is the low pass filter trying to do for a very high frequency? It is trying to just divide by omega naught RC. Therefore, if you consider the effect of this low pass filter, right, the input has got scaled by omega naught and the low pass filter is now trying to divide by omega naught, and therefore the two omega naughts will cancel out each other, and effectively the output of that low pass filter will just be a sine omega naught t plus phi or a cos omega naught, it does not matter, right? The amplitude will remain unchanged, right? And that is the key point that I want to highlight here. And therefore, if I took the case of the low pass filter, right, you know, for the low pass filter, and I did this amplitude of t as a function of the frequency, it would go like this. For very low omega naughts, right, omega naught squared r squared c square is negligible compared to 1, and therefore the input will remain unchanged, right. Even the phase shift tan phi omega naught rc, if omega naught is 0, then there is no phase shift, right. If it is a very small number, very small phase shift. So the amplitude will be remain the same for lower frequencies, it will start dropping as you go to higher frequencies, right. On the other hand, if I now took the case of the low pass filter, high pass filter that I am talking about here, and I did the same plot, mod of V naught of t as a function of frequency, right. Like I said, for lower frequencies, you are, first of all, you are killing the amplitude because you are doing a naught, a into omega naught. So if omega naught is very small, right, you are just killing the input itself, right, you are just killing the input, and therefore you are feeding almost nothing to that system. That means nothing else, nothing will come out of that system either. So, okay, so you are going to kill the input at this point, and then the low pass filter will just pass it as it is, right. So therefore it will come out with nothing, right. But as you go to higher frequencies, the input is getting scaled by omega naught, the low pass filter is trying to kill it by omega naught, and therefore it will come back. So this amplitude here, if this is A, right, it will come back to A here, okay, the amplitude. This is the low pass filter, and this is my high pass filter, right. So these two are sort of very nicely, you know, are behaving in a very similar manner, but they are operating on different inputs, and therefore you see a different behavior. So intuitively, it is very evident that this has to behave like a high pass filter, which means higher frequencies go unchanged, it is the lower frequencies that are going to get killed, okay. Now that is about the theory, just about the thing. Now coming to this, you know, the kit that you are trying to do here, the experiment that you are trying to do with the kit, okay, it is very important to understand this. So from the AD-ALM kit 1000, right, from channel A, let us say from channel A, you are trying to generate a sine wave and you are trying to give it to my high pass filter, okay. So the resistor and capacitor is basically on the breadboard, okay, this is some C, this is R. Now what is the output that you are going to get from this AD-ALM kit, first of all, right, what is the sine wave? So if this is V in of t, right. So if you look at the sine wave that is going to come out of this, it is going to be like this, right. This is the voltage, so this is 0 volt and this is 5 volt, okay. So what is going to happen is, first of all, the AD-ALM 1000 kit is going to give you a input voltage which is very different from the sine wave. The equation of this wave is not A sine omega naught t. For example, A equal to 5 volt and whatever the frequency, this is not A sine omega naught t. This is something else, because A sine omega naught t would effectively look like this. Yeah, this is how, you know, approximately my A sine omega naught t would look. This is, you know, A sine of omega naught t, okay, where this is, I am saying this is equal to A, okay. But if I want to obtain the black curve, then the whole thing needs to be shifted up. So the equation of this guy is actually A plus A sine omega naught t. okay, and therefore this amplitude 5 volt, 2A will be equal to 5 volt, and therefore A will be equal to 2.5 volt. So first thing you must understand is, in the case of a low pass filter and the high pass filter, you were giving a different input from the an actual sine wave. We did not give A sin omega naught t as an input to the differential equation. We gave A plus A sin omega naught t, okay, and the low pass filter did something with it, you got the output appropriately and stuff like that, there was no issue. In the high pass filter you are going to observe something very interesting, and it is very related to the fact that you are now feeding A plus A sin omega naught t to the high pass filter. So what is this A, right? So my V in of t is actually A plus A sin omega naught t, right? So first of all, it is very easy to see that if I pass this A plus A sin omega naught t through the derivative block, through this derivative block here, it will just kill the A. It's a constant with respect to time, okay? Therefore that is simply going to go, and you will only get A sin omega naught t going into the low pass filter. That will get low pass filtered and you will get some output. So that's the reason that even though from your ADALM kit, okay, even though you gave V in of t like this, right, even though you gave a voltage like this, the output from this kit, right, assuming this is very high frequency, will end up looking like this, okay, and there is this negative part, by the way, but the ADALM kit cannot show you the negative voltage, and therefore you will not see this part, you will not see this part, you will only see this half thing, right, you will only see this thing. This voltage will keep repeating like this, you will only see the positive half cycle, not the negative half cycle. And now that one way to look at this is to just say that, yeah, like I told you, it's going through a derivative block, the derivative will kill it, and therefore it is going to essentially give you only the A sin omega naught t's response, which is basically going to be centered around the origin and not around 2.5 volt. So this is 2.5 volt, this is 5 volt, this is 0. So therefore the sine wave will be centered about 0 and not about 2.5 volt, okay. Now your job is to find out, first of all, analyze and find out why this is happening from the differential equation point of view also, and your job is to now get this guy back up here. I want you to get an output as shown in magenta here, assuming again this is very high frequency. I want the output to come out unchanged. If you give a lower frequency, then it will end up getting clipped like this, and also there will be a phase shift. This will be for lower frequencies, okay. The magenta is, if it is a very high frequency, the output will just follow the input exactly, okay, assuming there is no phase shift or any change in the amplitude either, okay. So to do this, you need to change something in the circuit, okay, and of course now how do you analyze such a thing? By the way, A sin omega naught t, A plus A sin omega naught t, you can use superposition theorem, okay. It's like just giving A sin omega naught t first, right. So if you look at this particular input that we are giving to this high pass filter or the low pass filter, actually it doesn't matter, right. It's like this, this is A, this is my sinusoid, A sin omega naught t, and then I am giving it to the low pass filter or the high pass filter, okay. Now to analyze this, you can do this using superposition, because you first assume there is only the DC voltage A, find out the response of the filter, then you assume that there is only A sin omega naught t, no, the DC is absent, find the response, add the two of them, you will get the output, right? This is how you have to analyze using superposition. So you do the same thing even with the high pass filter, where you basically take this A sin omega naught t and give it to the high pass filter. This is R, this is C, this is my V out of t. So you have to do something. Now you have to change this circuit somehow so that V out of t is shifted up by 2.5 volts. Okay, that's your job. Figure out how to do this and analyze why that should work. The hint is you will have to add a voltage source somewhere for some value, figure out what the value is and where you have to add it, and then you can use a third level of superposition to solve all of these three things together. Okay, that is going to be the job that I am going to sort of leave it to you to figure out and find the solution analytically. So the main thing, the message that I want to convey here is, one, you must know how to derive everything mathematically, right? You should do the differential equation, exact things you should match. Then you should also know intuitively why it, why it happens, what is happening and stuff like that, right? And then you should also make sure from a circuit perspective that it works, right? So intuitively you know, okay, this solution should work, right? But you got to go and demonstrate on the circuit that it actually works and it works exactly as expected. This is the methodology that you will have to adopt even for doing research in general. Because when you're doing research, you do not know the output, you do not know what to expect. It's an unsolved problem that you're working on, and the only way to be sure that you are on the right track is to look at it from various angles, from the mathematical rigor perspective, from the intuition perspective, from the circuit perspective, superposition. All of these should give you the same answer. Only then are you guaranteed that you may be on the right track. If these answers don't agree, then there's something wrong. You're surely not on the right track, you need to go and fix it. But if you are on the right, but if all these things agree, it's likely you're on the right track, okay? And that's why we want to hammer this into you right from day one in this program, okay? So go ahead, get the high pass filter working so that you get a full, rail to rail voltage swing, 0 to 5 volt. Fix your circuit and analyze it and understand how to get it working. Okay, thank you.